In this video, we are going to discuss how we classify matter. We typically divide matter into two different categories: pure substance or a mixture. Under pure substances, we put those forms of matter that have a constant composition and they have distinct properties that sets them apart from other substances. Let me give you an example. If I have water, that is a pure substance and it has a constant composition. It is made of 2 atoms of hydrogen and 1 atom of water or of oxygen, and it doesn't matter where it is found on Earth. It can be, or even in the sky. It can be here in the States, it can be in America, South America, it could be in Africa, it could be anywhere, and it's water because it has 2 atoms of hydrogen and 1 atom of oxygen. That doesn't change. It also has distinct properties. Water doesn't have color or smell or much of a taste, but it has other characteristics that set it apart from different compounds, different pure substances. It boils at 100 degrees Celsius. It melts at 0 degrees Celsius, etc., etc. So every pure substance has these distinct properties that set it apart from other pure substances. A mixture, on the other hand, is made up of 2 or more substances put together, pure substances put together. And I can also change the composition of the mixture by varying the proportions of the 2 or more substances that I have mixed together. If I have water and I grab some sugar and I dissolve it in that water, then I have a mixture. I have 2 different compounds that I'm mixing together. If I have water by itself, that's a pure substance. If I have sugar by itself, that's a pure substance. But once I put them together, now I have a mixture. And I can vary the proportion of my mixture. I can have 1 teaspoon of sugar in 1 cup of water, or I can have a 1/4 cup of sugar in 1 cup of water. And it dissolves, and I have a sweeter mixture, my second one, than my first one. Now this should hopefully be review for you. All substances exist in 3 different forms. It's really 4, but we're not going to talk about the 4th one. We are going to categorize the substances in these 3 states of matter. So solid, liquid, and gas. We are at least familiar with solid, liquids, and gases from just experience. But what is the difference between these 3 different states? When I look at a solid, those atoms or molecules that make up the solid are so closely packed together and they're very ordered. Most of solids exist in crystal structures, so they are very ordered and they don't have much space to move those atoms or molecules because they're so tightly packed, they can't really move. It's similar to if you've ever been in a big crowd, you have very little space to move, so you don't have much freedom, and you kind of move with the crowd. This is the same idea of what the solid particles look like. And we say that the particles have very small kinetic energy, which is the energy of movement, because they cannot move very much. When we move to a liquid, those particles are also kind of held close together, but not very rigidly, not as rigidly as the solids particle. They're not as close either. This allows the liquids to conform to the shape of the container, so they become pourable, whereas the solid is not pourable. Those particles, since they are not as close to each other, they are not as attracted to each other, and they are freer to move, so they have a little bit higher kinetic energy than the solid particles. Lastly, the gas particles are very far apart compared to the size of the atoms or molecules. And those molecules or those particles are moving so fast that they don't really feel the interaction with other molecules or the attraction with other molecules. They have high kinetic energy. They're moving very fast. This allows gases then to conform not only to the shape, but to the volume as well, to the size. They fill up the whole container, not just the bottom like the liquids do, but the whole container. We can take a substance from a solid, convert it to a liquid, convert it all the way to a gas, without changing the identity of the substance. So when I'm taking ice, which is solid water, and I melt it to make a liquid water, and then I evaporate it to turn it into a gas, it is still water. It has the same composition, so I don't change the identity of my substance, but I am changing the state of matter. It's going from a solid to a liquid to a gas. Here's kind of a pictorial of what those particles look like in a solid and liquid and a gas. Here's how tightly those particles are arranged, very orderly, if you can see, and they're very tight, and therefore there's not a whole lot of room here to move. That's why the solids are very rigid, and they don't take the shape of the container. When I'm looking to a liquid, these aren't so very orderly now. Those particles are not tightly packed. They're still packed in there, but not very tight, or as tight as the solid. And those molecules have a little higher kinetic energy, and they can move a little more than those of a solid. And finally, when I move all the way to a gas, those particles are moving quite fast. They have high kinetic energy, and the distances between them is pretty large compared to the size of the particles themselves. And they take, as you can see, the whole shape of the container and the volume, and those particles are much freer to move than in the liquid or solid phase. Let's focus our attention on mixtures. Mixtures, we said, are a combination of two or more substances. Both substances, though, or whatever substance I'm mixing together, they keep their identity. So I'm not changing the identity of whatever pure substances I'm mixing together. When I have sugar water, I still have the sugar in there and I still have the water. I have not changed them into different compounds or different molecules. So when I make a mixture, that is not a chemical reaction occurring. In a chemical reaction, I take my original substances and I convert them into something else. When I make a mixture, I still retain those substances that I'm mixing together. We can subdivide mixtures into two different categories as well. They are homogeneous or heterogeneous. Homogeneous mixtures are uniform throughout. I cannot tell this is the particle of one substance and this is the particle of another substance. So I cannot tell apart the particles. Let's take an example. Air. Air is a mixture of several different gases, but I cannot say, well, this is an oxygen molecule, and this is a nitrogen molecule, and this is a helium molecule, and hydrogen and water vapor, whatever. These gases are not separate. I cannot separate them from each other. They are uniform. They are very well mixed together. This is what makes a homogeneous mixture. If I'm looking at the sugar water, I cannot say, well, this is a sugar particle and that is a water particle. I can't do that. Maybe if I were to look through very, very microscopically, but it's impossible with the naked eye. And so those are homogeneous mixtures. Heterogeneous mixtures, on the other hand, obviously would be those mixtures that are not uniform. If I have sand water or muddy water, I can tell the particles apart. I can say, well, this part is water, this part is sand. Even though they're mixed together, they're not uniform throughout the mixture. If I have iron filings that are mixed with sand, they are not uniform throughout, and I can tell which particle is which. They don't mix at the very microscopic level, at the atomic level. They don't mix very well. Mixtures then can be separated into individual substances without changing the identities. So just as when I'm making a mixture, I don't change their identities. When I separate the parts of the mixture, I still retain their identity. For example, if I want to separate the iron filings from the sand, all I have to do is just take a magnet and I get all the iron separated from the sand, because iron is magnetic and sand isn't. But I still have iron and I still have sand. I did not change them into something else. I just separated them out. Similarly with the sugar water, I can make the sugar or the water evaporate and I can collect it, condense it into a different container. So I can separate the water from the sugar crystals. I still have sugar and I still have water, but they're not together anymore. They're separate. When I talk about substances, I talk about their properties and their composition. When we measure properties in science, we can have two types of measurements. They can be quantitative or qualitative. Qualitative measurements do not require a measurement with a number. We don't need a number. For example, if I am talking about the color of a metal, I am not measuring it with a number and a unit. I'm just saying that copper is reddish in color, for example. That is a qualitative property. And I'm not measuring it with an instrument and expressing it with a number and a unit. Quantitative measurements, on the other hand, are measured and expressed with a number followed by a unit depending on what I'm measuring. For example, if I'm measuring the melting point of a substance, of water, I take a measurement, so it's quantitative, and it's expressed with a number. So let's say for water it's 0, and it's followed by a unit, which is degrees Celsius. I can also express it in Fahrenheit, or I can express it in Kelvin, but it's still a number followed by a unit. So those are quantitative measurements. When we describe substances, we talk about their physical properties and their chemical properties. What is the difference? Physical properties are those properties that we observe without changing the identity of a substance. So when we do the measurement, we're not changing it into something else. Some examples include color, or melting point, or boiling point, or density, physical state, etc., etc. Color of copper, for example, that's a physical property. I can observe it without doing anything to the copper, without changing it or combining it with something else to give me a different compound. A physical state change, for example, going from solid to a liquid or a liquid to a gas, that is a physical change. Like melting, for example, it's a physical change, a physical process. I do not change the identity of my compound or my element. A chemical property, on the other hand, can only be observed when there is a chemical change or a chemical reaction that occurs. Here's some examples. We're looking to rusting or burning in the air. We should be familiar with rusting because we live in the northern country and our cars rust eventually over years. When the car rusts, we do not have the original compound any longer. It has been converted into a different compound. When we burn something in oxygen, in air, we do not have, let's say you burn a piece of paper, we don't have the original compound at the end of that chemical change. We have ashes and we have water vapor, so it depends if it's a complete combustion or not. But we can have several different products, but none of them look like the original products. And so we have a chemical change or a chemical process. The original substance is no longer there after a chemical change occurs. Now here are two sample problems for you to try. Which of the following are pure substances and which are mixtures? I am going to set these up so that the first question you're going to answer is which are pure substances, and if there are multiple correct answers, you need to select all of them. Which are mixtures? If there are multiple correct answers, you need to select all of them to be able to continue to the next question. The last sample problem, which of the following are physical properties and which are chemical properties? This will also be set up similarly as the previous sample problem into two different questions. The first one will deal with physical properties and the second with chemical properties. Pick, if there's multiple of each, then pick all physical properties in the question, or pick all the chemical properties in the question to get the question correct.